hundreds of millions of years ago, these were both homologous. This pair were originally homologous autosomes. Okay, that's back when they occurred in our reptilian ancestor. And in those days, long ago, so somewhere around 300 million years ago, gender was determined by temperature. And there are some reptiles where that continues today. And there are other vertebrates where gender is rather plastic. And some organisms, some tropical fish start life as a female, become a male later on. So a lot of plasticity here, but not for us. We are pretty much determined by the inheritance of the sex chromosome by the sperm cell. Although, and I won't get much into gender because it's a little more fluid than people give credit. All of us have a combination of both gender hormones, and the proportions of the two are vary in people, and some people truly are more of a mosaic in terms of gender than others. So that's not necessarily a lifestyle choice, but a biological reality. We're talking about, I'm going to talk a little bit about X and Y, and I'm going to show you a small part of the lecture from the Howard Hughes Medical Institute on the evolution of Y chromosome. It's kind of interesting. So let's talk about the X chromosome first. I said this is something that I mentioned at the end of Monday. This is one of the most gene-rich chromosomes in the human genome. It has roughly 10% of all human genes on this one chromosome. That's somewhere around 1,100 genes. That's the number I see in different publications. Mostly unrelated to being a female. Okay, and I already talked about many of these. These are some of the better known genes, especially those that are expressed when they're in the mutant form in males. We talked about that is they are some of the more important X-linked recessive traits. And as I described earlier, a lot of genes are known by their mutant version because when there's a mutation in the phenotype, in the wild type version of the species, we often want to wonder what is the origin of that mutation, what is the genetic origin or lesion, and then that helps scientists to track down the location of the gene and study the particular misspelling of the gene, and that will lead to correction through gene therapy or gene editing. Talked about some of these already, like dystrophin is known in its mutant form as a gene that, when mutated, produces this debilitating disease called muscular dystrophy. This is a gene that leads to malformation of the ectoderm, skin and hair and teeth. This gene contributes to the immune system, and when mutated, contributes to the severe combined immunodeficiency syndrome, very severe condition. I'm going to talk about this in the next slide or so. These are some of the genes involved in blood clotting illnesses. Of course, now people that inherit these mutations, can, at least men, can survive a more robust, healthy life because these protein products, gene products, are now available, generated through molecular biotechnology. And then some of the colorblind genes here near the tip of the X chromosome. I did mention yesterday a little bit, or Monday, talked about some of the issues in terms of what's called gene dosage. Okay, the more copies of the gene you have, the more protein product it can produce, and this is can be an issue between males and females because, well, could have been, it's not, because of course females have 2 X's and males have 1 X and a Y, and the X and Y are no longer really homologous. That's an ancient condition. Homologous chromosomes, the matching set in terms of size and appearance, with the same ordered sets of genes. X and Y share very few genes, which means they really don't recombine. They do form a tetrad in meiosis prophase 1, but almost no recombination occurs. Okay, that's actually is detrimental to the existence of the Y chromosome, because if 2 autosomes can recombine, sometimes a mutated gene can be replaced by a healthy one from your homologous partner. But if you don't have anything to recombine with and you have a mutation, you have to live with it and pass it on to your offspring. So that's a disadvantage of not having an homologous partner. Okay? The other thing is that, again, with gene dosage, females have 2 X's. Now, of course, they got one from their mummy, one from their pop. So they may have different alleles in these genes for some of these different conditions. For example, maybe from mother they got a mutated gene for hemophilia B or A, but dad gave them a good version, so they're not a bleeder, they're just a carrier. They're maybe dangerous for some of their children. So having a pair of X chromosomes is to mask some of those mutations, where males aren't so lucky because there's not a homologous partner on the Y chromosome, except there are very few genes there. Okay. Now, to help balance gene dosage in mammals, particularly in primates, soon after conception, somewhere in early development, let me just give you a little, just very basic embryology, but this is the sperm cell, and there's the egg, and they fuse. The first stage of fusion is called a zygote. And then it goes through rapid cell division within 24 hours, where cells divide really fast and produce a ball of cells. That process is called cleavage. And about the 100 cell stage of that early embryo that we all went through, for you females, in different cells, some X's start to turn off. They become inactivated. So there's something called X inactivation. And that's so that every cell in your body, ladies, only has really one functioning X. So you have the same gene dosage as we males. Now, when this happens in the early embryo stage, when you're about 100 cell embryo, somewhere around that, it's not exactly, okay? When these X's start to turn off in different cells, it happens at random. So not all the X's turn off in all the cells. So ladies, you are a genetic mosaic. Your cells, your body cells, are not identical to each other in terms of what chromosomes they have, mainly because of your X chromosome. In some cells, you have the X working from mommy, and in other cells, you have the X working from daddy. Okay, and so you have kind of a sort of a mosaic composition. For example, there are some women who have a mutation in a gene that helps to produce sweat to cool the body down. And if and that's on the X chromosome, which means that in some patches of their skin they sweat, other patches they don't. So they're really mosaics. We're not, because we only get one X from mom, right? So all our cells are more or less exactly the same, where females are mosaics. Okay? And this inactivation is to maintain the proper gene dosage, so you only have really one set of X chromosome genes versus 2. Because differences in gene dosage sometimes are detrimental to the proper functioning of the cell. Does that make sense? And that gene, and this X inactivation is triggered by this gene right here, the ZIST X chromosome gene. Okay? And the way which cell as these 100 cell embryo stage starts to turn X's off at random in different cells, it's not understood, as far as I know from the reading I've done, how it chooses which X to turn off. Okay, and when it's turned off, it kind of shrivels up and compacts into a very small compact structure you can visibly see. It's called a bar body. That's the compacted X chromosome that's packaged away and never used again. And as that cell divides the daughter cells, of course, at 100 cell stage, you're going to go through trillions of cell divisions to produce a trillion cell body. And all the descendants of these different cells, they always keep the same X off. So once it makes that selection, that X is never turned on in all of its descendants. Yeah.
So this is the X's?
This is the gene that causes that.
Okay.
Okay. And what it produces at this 100 cell stage, it produces this ZIS gene. It produces a long non-coding RNA molecule. That's what that stands for. And it binds to the chromosome and really compacts it, really covers it up, pulling a sheath over it. It causes it to compact in this very small, tight structure called a bar body. Those genes are off. Most of them. Actually, some of the genes are left on because it covers most of the chromosome, but not completely. But mostly it inactivates most of the chromosome. And it does it at random. Okay? So kind of an interesting mechanism to maintain gene dosage. Yeah.
The bar body will be staying in your
Well, it's a chromosome. It's a compacted X chromosome that's in every nucleus in the female.
Which just isn't, you know, use it as inactivity.
It's to maintain the appropriate gene dosage. It's the normal function, normal event in the development of a female. Again, that means that in every cell in your body, ladies, you only have one functioning X, just like we men do. Except in your cells, they're not all using the same X. Some are using the X from mommy, some from daddy. Yeah.
If they stay compacted, does it mean you can always see the X chromosome?
You can see the bar body when you look at I believe in I don't know if you have to look at an electron micrograph or you can look at a mitotic a metaphase cell, but they're visible for sure. Now here's evidence. This is the example your book gives about X inactivation. Sometimes you'll see this is a calico cat with this splotchy fur pattern. Okay, and there are a couple of genes controlling fur color here. A couple we'll talk about. The one that produces orange fur, that gene is on the X chromosome. Okay, and so here we have. So here you can see again, because of this inactivation, X inactivation, one of the X's is functioning, and here's the other one that's been compacted because of the expression of this gene producing this bar body. And so any gene on here is not going to be available to control the phenotype of the individual. We see that, so in the orange splotches, referring to this cell here, we see that the animal is, the calico cat is heterozygous for a gene that produces orange fur. Okay? Here we see on the functioning X, the allele for the orange fur color is functioning. It's a functioning allele, but on the